I just published an episode talking about AI and its ability to learn on its own without any human interaction. I ended that episode by talking about how I don't think models like this exist, and saying that if they do, I don't see that they are going to be out in production. And then one day later, I come across this. A paper just published one day ago talking about AZR, the absolute zero reasoner, basically a way for models to learn on their own without any hand curated datasets or human interaction. So, was I entirely wrong? Let's dive deep into this AZR paper, try to explain what it is and how it works, and maybe then we'll get an idea on if that breaks what I already said last episode or if I'm still on track. First things first, what is AZR and who really built it? Absolute Zero Reinforcement Self-Play Reasoning with No Data is a paper published by researchers from the Tsinghua University, Beijing Institute of General AI, and the Pennsylvania State University. It's a paper focusing on the use or the creation of models that are able to learn through no data at all by having just the model learn and interact by its own. They compared that to reinforcement learning with verifiable rewards. Now, we already talked about reinforcement learning and how it works, and how the model basically receives an observation, provides an action, and gets a reward. Now, this reward is positive or negative to explain if the model has done something good or if it needs to improve, and then the model tries as much as it can to get the most positive reward that it can. Now, these rewards are given to the model as a fact. We assume that they are given without any mistakes. However, in reality, there is always noise, and if they're given by humans, there is inconsistencies and mistakes that could happen with writing these reward functions. This is why when building a reinforcement learning agent, sometimes you would go back and forth a lot of times to make sure that the reward works. You would train the model, look at how it acts, and then the model would react to your different reward functions. And this is where verifiable rewards come in. The idea is that instead of having a human just hand curate all rewards, we assume that we can use a algorithmic or procedural or factional way to make sure that the reward is verifiable. Think of it like using a compiler for your code. Basically, when you write code, you can give that to a compiler that tells you if the syntax of the code is correct, meaning that it will run. And you can also use tests or run the code to actually confirm that the result you're expecting comes out. So this is how you can confirm the logic and the syntax of your code by using something that is verifiable. And for mass equations, this could be something like a given theorem or some actual given mathematical formula. So if you come up with your own mathematical solution, you can confirm if some proof verifies this equation. Now, this RLVR, reinforcement learning with verifiable rewards, has already been used with LLMs to make sure that they get better in reasoning. However, it still really depended on having some hand-curated dataset. So it still needed some input output pairs for the model to train on. And what the researchers are doing with this AZR is that they're trying to make sure that there is no need at all for this hand curated data set. So, how does it work? Well, the model gets to be the proposer but also the solver. Basically, they use the model as the question giver. So the model decides on its own what kind of task to solve, and then the model also solves that task and then gets better in proposing tasks, but also gets better in solving them. So let's look at how the training loop works. Basically, it has two different stages, the proposal stage and the solving stage. In the proposal stage, the model proposes a task. The environment then takes that task and transforms it into a problem. This problem has an input output pair. In the second stage, the model then takes this problem and comes up with its own solution. This solution can then be compared to the solution that was already given by the model in the beginning as well as the environment. After which, the model receives two rewards. A reward for proposing a solution given by verifying if it's solvable. So this is a reward making sure the model can keep only proposing problems that are solvable, and then it gets better at proposing new tasks over and over again. And then it also receives a reward for solving the problem. And then the model can get better and better by solving more problems as it goes along. So let's talk about the results. The model used 6 benchmarks for math problems as well as 3 benchmarks for coding problems. And these were used to test the model's results after it's been trained. The results show that the model actually outperforms most state of the art methods when it comes to coding problems. However, it does not perform better on all math problems. When you get the overall average for all problems, the model does perform better than all other state of the art methods. So, this proves that models that train by themselves are able to outperform most models in a lot of tasks. So you might see this and be thinking to yourself that AI has evolved and is now able to train by itself with no hand curated knowledge at all. But there is a twist, something that the headlines don't really talk about. This new paradigm, while is great and gives us really good results, does need a pre trained model as a base model to start the training from. Meaning that the model, before it even gets into teaching itself, has already been taught by someone else. The models that they used are based on Quen and Llama, and they're already pre-trained and available as models that you can use. They also explain that models with more coding experience perform better on coding tasks, which makes sense. That means that also models that are trained more on mathematical formulas will outperform models that are not, or let's say models with less experience on these same tasks. This basically means that while the models are great at improving by themselves, they do need a starting point. They do need a model that is trained on some way or form before it gets to the point that it needs to further improve. Let's take a step back and look at the bigger picture again for a bit. Let's take a look at one of the examples given in the paper on some coding tasks. The model is given some snippet of code as well as an input-output format. The model here in this example is trying to learn abduction. Abduction, for those of you who don't know, is a way of explaining an observation given to the model. Basically, it's reasoning on what is the best explanation that can fully explain this observation. So in this case, given a code with some input output format, the abduction could try to explain why this code works like that. So this explains by showing some different inputs to the code or explaining how the code works. Now, let's assume that the base model they're using has never seen code before. It was not trained at all on any coding examples. This means that the model will not only struggle to come up with an explanation of the code, it will be very bad at generating this code, because how can you generate something you've never seen? Now, for Python code, maybe it's easier to look at and explain, but for code you've never seen before, like C++, for example, these codes are way harder to explain than different kind of code. And then for a model that has never at all had an experience with this, it will be, dare I say, impossible to generate this exact code snippet. Now, considering that the model only gets the reward function, because again, it's still reinforcement learning, it's still learning on its own, so the only output it really has isn't the solution, but rather the reward. This could be very complex. It could take way too long time, if ever, for the model to learn to do this on its own. Like, for example, assuming that you only have access to a compiler that tells you whether or not the code you've written is true or false, you write your own code and then you receive a reward that tells you, hey, -5 marks, the code doesn't work. Now, I'm not very sure if internally the model also gets the entire explanation. I assume it does, which means you could try to learn by doing this over and over again. It will just take way too long. It's trying to learn something from zero knowledge at all, and I'm not sure how fast models with zero knowledge are able to get to that point. Now, the paper also touched on the topic of LLMs using more than just code and mathematical functions as verifiable rewards, and this includes getting information from the internet. So, taking this into consideration, maybe the model will be able to call some internet link and then get some information from that, maybe some examples to get it started. But again, the model needs to learn to already be able to get information on how to call the tool, how to call the internet, and how to receive the information, as well as how to understand the information within it. These are stuff, like I explained, are not available to LLMs by default. So while yes, this new paradigm of training causes the model to improve beyond some state-of-the-art models, but there are some points to consider. Most notably for me is the question of how good the model needs to be before it goes into this improvement step, and how much knowledge does it need to have in the tasks that it's trying to solve. I don't think this exists notably within the paper, but it would be something to consider for further improvements. Now, again, this kind of paper is quite a good improvement and it's great when it comes to the research behind it. But I find it very bad to think about the way people talk about it as, oh my God, this is so scary. Be scared of AI. Because again, while it does learn to improve on their own, having the capability of the model to decide on what is the good task to learn from and how to solve that task is great. Because again, the model improves by learning tasks that it hasn't been trained on, or at least has already done bad on before the training, which is great. But these models are still kind of not in the sense of models that were never trained at all before. You still need a starting point. Now, there is actually something else to talk about here. The researchers noted that the LLM Llama 3.18b sometimes produces very concerning chain of thoughts outputs. They termed that the uh-oh moment. And basically, what happens is that the model produces some text in its chain of thoughts and its reasoning that they deemed very concerning when it grows into the learning strategy because the model could just learn to keep producing this. They said that while this paradigm allows the model to improve its reasoning without any, let's say, curated data sets, it still has some things to be aware of and it still needs to be managed and monitored by someone else. Basically, they said that it requires oversight to make sure that it does not show undesirable behaviors, which circles back into what I said about models that learn on their own without any hand curated datasets or more human interaction cannot go out there in production without any monitoring. Now, what I also think is important to say is that while all headlines are talking about AI learning to do something by themselves, this is specific for LLMs. Now, again, AI systems are a lot more than just the umbrella of LLMs, and this specific reasoning is only specific for LLM models, which are not widely used for every single task out there. But what do you think? Do you think I was fully wrong, or am I still, in a way, kind of right? Let me know. And subscribe if you find this informative, and maybe send it to someone who might be interested as well. And I'll see you in the next episode.